Good afternoon. My name is Mo Jetty, and I'm the chief architect and one of the main developers of Slurm. I started working on it 10 years ago, and I'll be reviewing its design with you today. The goals here are to teach you the basics of the Slurm architecture. It's only going to last a couple hours. We're not going to get into a very detailed description of it. But by the time you leave here, you should understand the architecture, what the daemons are, the commands, how to use a basic set of commands, learn how to build and configure and install Slurm with a simple configuration. And there are volumes of documentation available, but this should give you a good introduction. In terms of the agenda, I'm going to start off with what the roles are of a resource manager and distinguish between a resource manager and a job scheduler, then go over the Slurm design and its architecture. I'll be spending most of my time on that. Then go into what the commands are, go over a simple build and configuration, and then at the end, I'll get into more detail about the Slurm plugins, which are related to job scheduling, and Slurm development work, which is one of your interests here. And feel free to interrupt if you have any questions. So what's the role of a resource manager? I'm distinguishing here between a resource manager and a job scheduler because some architectures really do distinguish between them. You can think of a resource manager as the glue that makes a parallel computer execute your parallel jobs easily. It turns a set of hundreds or thousands or tens of thousands of computers into a single unit that you can easily run jobs on. And ideally it makes a parallel computer as easy to use as a PC. And a simple example here on a simple computer, you might just type a.out to execute the program a.out. And on a cluster being managed by Slurm, you will precede your program name with typically a command like srun, how many tasks you want to run, and Slurm would take care of allocating resources, launching them, binding them to tasks, doing everything it needs to get your MPI communications running for it. So in a little bit more detail, it's allocating resources within a cluster. So the things that Slurm is managing are the nodes, which we typically consider a unique IP address. It's keeping track of the architecture within a node. So for example, the NUMA boards, the sockets, the cores, the hyperthreads, the memory, the interconnect, and generic resources, which would be things like a GPU. It's managing licenses, and it's launching and otherwise managing the jobs. When there's more work than can be handled by a computer, you would typically need a job scheduler. And in some architectures, this is a level up above your resource manager. So it's supporting complex scheduling algorithms, so optimizing for network topology, fair share scheduling, advanced reservations, gang scheduling, and so forth, various limits by queue and user and group. Some batch systems provide both of these functionalities within a single entity, like LSF, and Slurm does as well. In other instances, they are unique products. So if you look at the Maui or Moab scheduler, that's a scheduler, and it can't run independent of a resource manager because it doesn't have the level of detailed knowledge about the architecture on a node and managing the network resources and such. So with Moab, you would typically run with, say, Torque or Slurm as an underlying resource manager. So next I'm going to go into the design and architecture, and I'll be spending most of my time on this. So what is Slurm? The acronym stands for Simple Linux Utility for Resource Management. And if you watch the Futurama cartoons, it's also a beverage in that. But Slurm isn't exactly simple anymore. It doesn't just run on Linux, and it's not just a resource manager. So we're getting away from the acronym and just calling it a Slurm workload manager. The development started in 2002 at Lawrence Livermore Lab, as a simple resource manager for use with a job scheduler that was developed at Livermore, which has since ceased to exist. And it's evolved into a very capable scheduler through the use of optional plugins. It's about 500,000 lines of code, so that's why you can't call it simple anymore. It supports AIX and Linux, Solaris, and other Unix variants. And it is used on many of the world's largest computers. At supercomputing, we went through the top 500 list, and we didn't get too far, but it looks like about a third of the systems running on the top 500 list are running Slurm, which is probably more than any other workload manager, because the rest of the systems are split amongst several other workload managers. In terms of our design goal, we wanted it small and simple. So depending on your configuration, it can be very, very small and simple. In fact, Intel has ported it to their cluster on a chip. And they went through researching what's the minimal configuration, what's the minimal set of plugins and architecture we can get away with, and so they did that. At the other extreme, Sequoia, which is not number one anymore, but number 2 on the top 500 list. It's a Blue Gene Q at Lawrence Livermore Lab, which is about 35 miles from here. That's has 1.6 million cores, and we're using Slurm on that as the job scheduler. It's not working with Moab or anything else. Slurm's doing everything on there. Now, it isn't actually handling the resource allocation over those 1.6 million cores. It's operating at the level of sockets on a Blue Gene Q. So it's actually handling the scheduling of 100,000 entities on that. And we've simulated systems 20 times that size. So we're really not seeing too much of a problem with scalability at this point, or for the foreseeable future. It's quite fast. The latest version of Slurm, which has even better performance than what you were testing on earlier, depending on your configuration, we can get up to 600 jobs per second throughput, and up to 1,000 job submissions per second. Now, on a more realistic configuration, the number might be half of that if you want to do accounting for everything and have a bunch of resource limits and such. But it is very fast. It's available under open source general public license version 2, and there is an active worldwide development community. We've recently surpassed 100 individual contributors to the code from all around the world, and there are quite a few different organizations contributing, and soon we should see some work coming in from Greenplum EMC. It's system administrator friendly, and I'll get into that a little bit more later, but the idea is we want the system easy for an administrator and for the largest clusters. So we use regular expressions for node lists, and a configuration file for a 10-node cluster or a 10,000-node cluster will look just about the same. Fault tolerant, which is really critical for a large system, no single point of failure, and highly portable because of the use of these plugins. Getting into the portability a little bit more, no kernel modifications required. It's written, well, 99% of it is written in C, and we follow the Linux kernel coding standard. It uses autoconf to adapt to the local environment. So, for example, when somebody wanted to port Slurm to Open Solaris, we didn't do that. They just ran autoconf that figured out what libraries were available, what header files were available, where they were, differences in functionality. And I think the port to Solaris took less than 100 lines of changes to the Slurm code, which is pretty good. The port to AIX took a little bit more effort than that, but it was not a huge effort. There's a skeleton of functionality within the Slurm, what I refer to as the kernel, and that's where about 2/3 of the Slurm code is, and about 1/3 of the code is in the form of these plugins. So if you want to add support for a new scheduling algorithm, a new network or whatever, that would typically take the form of a new plugin, and you can reuse the remainder of this Slurm code. As an example, I believe it was Rutgers University did some work to optimize scheduling for use of green energy. So if you've got a lot of solar or wind power available, they were taking weather forecasts and feeding it into a new Slurm plugin that they developed so that they could run most of their jobs when there was more green power available. Interesting idea. And there are a lot of system-specific plugins available. So for a Blue Jean system, almost all the logic for that is in a single Slurm plugin. For Cray system, virtually all of the code required to interact with Cray systems is in a Slurm plugin, which is only, I don't know, maybe 400 lines long or so. So plugins are dynamically linked objects. They're loaded at runtime based upon your configuration or your user options. There are about 80 of them available in maybe 20 different flavors. Some examples are, we've got an accounting storage plugin. How do you want to record accounting information for jobs? Do you want to store it in MySQL or Postgres or a text file? If you wanted to write it into DB2, all you would need to do is develop a new Slurm plugin that had the required functionality. There are plugins for different network topology, for a 3D torus and a tree torus. If we wanted to port to a system with a 5D torus, I mean, it would just be one new plugin, which would include just about all the logic. Something I'll mention about these is these plugins can be fairly large and sophisticated. Some of them spin off additional P threads that run and check state and do updates on a periodic basis. For example, the weather forecasting one, I mean, I presume it would go out and pull information about weather forecasts. So the plugins are typically loaded with a daemon or command starts, and they persist through the lifetime of that command, and they provide a level of indirection. Like I described with the accounting records, say when a job completes, there's a function that gets called saying, here's information about this job that just completed. And then the plugin decides what to do with it. Should you write it to a text file? Should you write it to a database? Should you write it directly to, to a Slurm daemon? I'll get into this. Should you write it directly to a database? Or maybe you don't care about the job accounting records. Maybe you just want to throw it away. It just gives you a flavor of what a plugin is. So all the plugins are documented, all the function calls that need to be supplied, the arguments coming and going, and most plugins have several examples available. So if you wanted to develop a new plugin, you would have several examples to look at. Some plugins also have a Lua scripting interface. So Lua is a scripting language that looks similar to Bash or whatever, but it's built to interact with C data structures. So this gives system administrators a relatively easy way of developing plugins for some cases without having to get into the C code or data structures. Here's a more detailed description of one of the plugins. There's a job submit plugin. It's called whenever a request comes in to submit a new job or to modify a job. And this can be used to set default values or enforce various limits. Say you want to interact with another database or whatever. So this just gives you the information about what functions need to be supplied. There's two. And the first one here is job submit plugin. what does the request actually look like? And you could use this, for example, to set default values. If a user submits a request and they don't specify a time limit, or they don't specify a job queue, you can say, oh, well, the job is so big and it's for this particular group, so we want them to run in this particular queue. The job modify is more or less just to handle updates to jobs that have already been submitted. But it does the same sort of functionality. Another example is a resource selection plugin, and there are several available. The first one we developed was to allocate whole nodes to jobs, which we called select linear. And HP had a need of allocating resources on a more fine-grained basis at the level of hyperthreads or cores or sockets. And they were actually able to do that with probably 90% of the code all in a single Slurm plugin. So going from allocating whole nodes to jobs to keeping track of and allocating at the level of cores or sockets, all in the Slurm plugin, which frankly surprised me. It was quite a feat that they were able to do something like that with relatively minimal changes to the Slurm kernel. There's another plugin which we have for BlueJean systems that interacts with IBM's BlueJean APIs. And there's another one which is for Cray systems that interacts with Bazel. I won't get into the details, but Cray has their own resource manager, and you're nodding your head, called Alps, and the interface to it is called Bazel. So we needed some means of interacting with that, but it also didn't have the sort of support for resource selection that we wanted. So what we did is we developed a new Slurm plugin which interacts with the IBM software, which is called Alps. But for the resource selection, we use an existing whole node selection plugin. So this is the select linear. So basically, this here is a thin layer that goes over our selection logic to select whole nodes and Cray. So when a request comes in, say a request for 2 nodes, this would use the Slurm plugin to select those nodes, and then it would in turn tell Alps, the Cray software, all right, I want to use node ID 4 and 5 for this job, and when it's ready, then it passes the information back up. So that's how it functions. And it's a few hundred lines, but if we needed to interface with some other new resource manager or new architecture, this just goes to show that it's a relatively simple process to do that.
So Mo,
yeah.
It's then you allow plugins to call plugins?
Yeah. Okay. There are many examples of plugins calling other plugins. So for example, I mentioned a Slurm topology plugin. Well, that's used by the resource selection plugin, for example. It is complicated.
I have a question here.
Sure.
If we write a plugin and want to reference to another plugin, how can we do? Or we can just simply reference to any plugin we currently have.
I didn't quite follow your question.
I think the question is, if I have, if you go back to your other slide, let's
sure.
Okay.
Sorry.
So that's fine. So when I'm calling a function out of the Slurm kernel, obviously there has to be a selection mechanism that says, well, we're using the Cray select plugin, so call that one.
Right.
But how does a function in there call the whole node selection plugin? Is it a unique? It's
yeah.
What
happens actually is the Slurm kernel is in its configuration file, and I hope this answers a question, but here's an example. It says use the Cray selection plugin, and the Cray selection plugin says, well, I need to allocate whole nodes to the job, so I am going to internally use this plugin, so it in turn loads this plugin. All right. If this plugin, the Cray selection plugin, needs to reference another plugin, say a node topology, but it doesn't know which one is configured, it would call the function in the Slurm kernel that would in turn already have linked up to it the appropriate underlying plugin.
So the Cray selection plugin specifically says load the whole node plugin, and then those function pointers are now instanced in the way that it can go ahead and call them. But it's not doing an abstract kind of call.
Is the dependency mechanism built in to the kernel? So like if you construct a plugin that requires other plugins, those are resolved or?
The plugins.
Is there a plugin packager, I guess, that you would load the plugins that would tell you to?
There's in the kernel basically a generic plugin mechanism that handles the resolutions of that sort of thing.
Can you give like a round number, like how many plugins there are?
Yeah, there's about 80.
80, okay.
That we provide with Slurm. There are other sites which have developed their own plugins for whatever purposes they have, and in many instances they're just site local things like I mentioned the green spot, the weather forecasting, and I'm not sure how useful that would be to the general public, but
actually it would be pretty. I mean, we've actually seen for us when we do jobs, right? It's there's definitely a power requirement for the job. So if you wanted to do it when it was cheaper, that would actually be useful.
Actually, I'm not sure I'm going to get into that right now, but the latest version of Slurm actually collects power consumption information per job and records that in the accounting database. And users, when they submit their job, can specify, I want to run the maximum frequency possible, or a low frequency, or whatever, which, our goal there is to eventually charge users for their power consumption as well as their resource use, how many processors they have, and use that in scheduling decisions to maximize the work throughput given a power cap. So that's coming. That's not available. Just the power consumption information is, and that's only in the latest version of Slurm. So the entities that Slurm is keeping track of right now are jobs, which you can think of as a resource allocation request, job steps, which are typically a set of parallel tasks. I know Ralph is intimately familiar with OpenMPI, so this is typically an MPI job. What we call a partition, you should think of as a job queue. It was named partition for historic reasons. Slurm was patterned after Quadrix RMS, and in their environment, nodes would be associated with one partition or another partition, and Slurm has since evolved so that it's really a general purpose job queue with various limits and access controls, but rather than confuse people and rename it, we kept the name partition. We're keeping track of the nodes which get allocated to the job, and Slurm is optimizing placement with respect to all these things. Your NUMA boards, sockets, cores, hyperthreads. So for example, if a job asks for a certain number of cores, we'll try to put those cores all in a single socket if possible, and if not, then try to pack it all on say, a single board. And users have options so that they can say, I want this all to be in a single socket, for example. So here's an example of the use of these. So users submit jobs to a Slurm partition, which again you should think of as a queue, and there are mechanisms of prioritizing these jobs. I won't get into them here. And when the job is allocated resources, it's allocated Depending on how you have Slurm configured, it might be allocated a set of cores on a specific socket on a specific node. And Slurm has task binding mechanisms, either C groups or CPU sets, so that the user can't go outside of the resources allocated to his job. And then within the job, I mean, if it's a batch job, it would typically be a script, something like this, and the user could run a couple of job steps. And again, these could be MPI jobs. And in this case, I've requested to run 4 tasks for the first step and 2 tasks for the second, and by default, we'll just divvy them up like that. So they get allocated separate cores. And if you're using Linux C groups, these cores are in those C groups. The memory allocated to the job is in those C groups. If you're allocating GPUs, those GPUs that have been allocated to the job are in those C groups as well. So if somebody tries to use more memory than they've been allocated, for example, they will have the malloc failure, but it won't affect any other jobs on that same node. The information that we keep track of for nodes we went over the resources. You can also just keep track of, you can allocate just CPUs if you want, memory size. We keep track of temporary disk space on the machine. Nodes can have associated features. So for example, this could indicate file systems or racks or whatever you feel is appropriate. There's a characteristic called weight, which you can use to favor certain nodes over others. And one way this could be used is, say you have certain nodes that have more memory than others. You could give the nodes with smaller memory a higher weight, so it's going to preferentially schedule jobs on those nodes with the less memory, unless somebody specifically requests a node with a feature of, say, big memory, or they specifically say, I need so much memory, in which case the only place it would be able to get that memory is on the node with the larger memory size. Keep track of boot time, so if we've got a job running and a node reboots out from under it, we can recognize that it's probably not still there. We keep track of the CPU load, which we don't use for scheduling purposes, but we do keep track of that. And then there's a state. If a node is configured down, either by a system administrator or by the Slurm system itself, there is associated with that a string, an arbitrary string, in which we keep track of why it went down, who put it down, and the time that the node went down. So if this is a good way to keep track of failed resources in large clusters. Here's a node state diagram. Your nodes typically move through this set of states. So it starts off idle, and then you allocate it to one or more jobs. And then when the job is finished running, it enters a completing state, at which point it runs an epilogue program. And when the epilogue is complete and all the processes are gone, it moves back to the idle state. There's a draining and drain state, which is for system administrators. Say you've got you want to replace some hardware that's failing, or you want to shut down a rack for relocation or whatever. You can put it in a draining state, and again you would keep track of the reasons, so you can easily see that. And if it fails hard, there's a down state also. Information about the Slurm queues and partitions. Your queue is associated with a specific set of nodes. It could be all the nodes, and nodes can be in multiple partitions. I mean, a typical scenario is you might have a set of nodes out. I'm thinking of a HPC center, which might not fit your model, but you might have a set of interactive nodes and then a set of batch nodes, which would be for your larger, longer running jobs. And then you might have a partition that includes all the resources in the system, say for running jobs across the whole system on weekends. There are job size and time limits, both in terms of minimum and maximums. So you can have a debug queue, for example, where you limit users to 10% of the nodes in that queue, and they can only run for an hour or something like that, so you can get more small jobs through during your working hours. There's an access control list. There are preemption rules available, so you can have a high priority queue. Slurm also supports qualities of service, which I think I get into elsewhere, but you can say typical scenarios, maybe you've got a standby queue for jobs that are of low importance, and if real work comes in, whatever qualifies as real work, you might have a preemption rule such that jobs in that standby queue can get re-queued whenever somebody else wants those resources. State information, which I think I go over in the next slide, and there are oversubscription and gag scheduling rules. So potentially you could say, I want to over-allocate each core by a factor of 2. So you can run 2 jobs per core and let the operating system sort out who runs when. Gang scheduling is you can think of it as time sharing for parallel jobs, really time slicing. And the idea there is you allocate 2 or more jobs the same resources, and you run them in turn. You would run, say job A, and then suspend job A and run job B, and then suspend job B and let job C run, and then suspend job C and cycle back over to job A. And what that lets you do, if you've got enough memory space, is it lets you get more jobs started so everybody can make at least some progress.
How tightly is that tied, I guess that's with, depends on vendor hooks?
Excuse me, what?
The gang scheduling?
Basically, all you need to do is support job suspend resume.
But like that would be, for example, I have a group of processes and I want to make sure like that they're all swapped in at the same time, right? That I was at Oracle, we had issues with this, right, where you have a queuing mechanism and one guy decides to go to sleep and then you're trying to send to him, and then the other process says, well, he's asleep, so I'll go to sleep till the guy wakes up, and because no one's sending, you're getting these weird...
Well, I mean, it's synchronized across all the resources for the job. Time slices for gang scheduling that are typically used are on the order of, say, 30 seconds or a minute. In some instances, there are hooks to the underlying MPI or network that tell it, hey, I'm going to suspend this job, just handle it. And then 60 seconds later, you say, all right, I'm going to wake this job, I'm going to suspend this other job, you stop it, and I'm waking this other job up, so you reset your timers or whatever you need to do. So that's what we do, for example, on the IBM systems.
I have a question here. How can we set up the over-subscription parameter?
There's a for each partition, there's a parameter called shared, and you can say what level of oversubscription you want. So if you want to have each processor allocated to up to 2 jobs, you would set shared equal 2:force. And the force basically means the user has no control over it. There's also a shared equals yes, which basically lets the user specify when he submits his job, I want to be able to share it or not. And after a job is allocated resources, within the job's allocation, the job step has the same sort of capability. So when I was doing the exclusive option, srun -- exclusive, a slide or 2 ago, that basically said, when I get these resources, I don't want any other job steps to be allocated those. So your job state information that Slurm keeps track of are an ID, which is just a sequence number. There's a name. There's a time limit. Users, when they submit their job, can say, I want this job to run for at least 30 minutes, but optimally for 4 hours. And what will happen is Slurm will schedule it as much time as it can, but if it can start earlier through backfill scheduling, what it might do is it might say, oh, well, I can start the job now, but I've only got 30 minutes, and the user says he'll take 30 minutes. We're just going to set the time limit to 30 minutes and get it started now. And he can handle resubmission. There's a size specification as well with minimum and maximum values. So somebody can say, I want 16, between 4 and 16 nodes, and then when it starts, I will decide how to manage those resources. Users also can specify in their job specification sockets, cores, threads, and so forth. Users can specify the nodes to be included or excluded from the resource allocation. So in the case of you're running and you suspect that there's a node that's flaky, you might say, well, I want 16 nodes or I want 64 cores, but don't let me run a node, tux 1, 2, 3, because last 2 times I ran over there, something bad happened, so keep me out of there. Users can also specify node features. I already described that, so you might say I want all my resources on rack 1, or there are also and or options available for that. So somebody might say, I want my job to run all on rack 1, or all on rack 2, or all on rack 3. Or I want nodes that are on rack 1 that have an Intel processor. So and or features like that. There are dependency rules. Run this job only after this other job completes successfully or after it fails. There's an account name, there's a quality of service, and then there's a state, and I think I go over the job state next. Yeah, so when you submit a job, it typically starts off in a pending state, and then it will go to a configuring state if you need to reboot a node. Say your nodes are down, or you need to boot a different operating system for the job or whatever. After the node is up and available, the job will go into a running state. If you're doing gang scheduling, it would alternate between suspended and running. Slurm has the ability to resize jobs. So after a job started, you can request additional resources to be allocated to the job. And what that looks like is a new job request. Here's a job request for an extra 64 CPUs because I think I'm going to need it later, and when it's granted, I want it to be merged to this running job. And then when the job is completed, there's a completing state which is used while the epilogue's running and when all the processes are being terminated. One important note is that when a job goes into this completing state, as the epilogue completes and all the processes are terminated on the nodes allocated to the job, as soon as that happens on any one of those nodes, those resources on that node are instantly available for another job. So if you've got a job that's allocated 128 nodes, for example, and there's some non-killable process because of a Lustre file system problem on one of the nodes, you can recover all 100. You can recover everything but that one bad node. And then after the job's completed, it would be in one of these completion state, whether it was canceled or preempted, failed, timeout, or whatever. Yeah, Ralph.
The resize feature, is that a blocking operation? If I call to resize, with that function call, is that block or does it call back asynchronously?
It's asynchronous callback. Job step. So within a job allocation, you would have the MPI jobs or job steps, and it's got a sequence number. Typically, that's listed as a job ID number, period, and then the step ID number. You've got a name, you've got a time limit. There's only one value for the job step, and the job step can have different time limits. So you can submit a job for an hour and then run a bunch of job steps which have time limits of 2 minutes each, for example. There are size specifications with minimum and maximums. and again, specific nodes to include or exclude, or features you want associated with that job step. Yeah. Sure.
Is it considered when people program or submit jobs to Slurm that they have kind of there's a known system configuration for them? Because I mean, I noticed you talk a lot about sort of specific node names or things like that. So my view is, for example, I have users with SQL queries, right? They have no idea, right, what's going on underneath. I have to provide a system that'll take those series, decompose them, and run them in parallel, right? But they're it's this question of what parts of the system will have sort of knowledge of system configuration and like, for example, I'd like to, it's more efficient if I can co-locate processes that are operating on data with racks that actually contain the data sources, things like that. So is that something Slurm can do, or is that something we have to kind of know?
Well, I mean, Slurm would be configured with whatever information you want to expose to the users. So if somebody specifically wants to run an Intel processor and somebody else specifically wants to run an AMD processor, they can do that. If they don't care, they don't care. They don't need to specify anything like that. But if you've got heterogeneity, then you can at least expose users to that. And if they want to have control over what specific types of resources they have, then they can
and in
get
one
that.
sense, that's something that we sort of do to isolate the users from that aspect of the...
Oh yeah. I mean, I think that very few users care at that level of detail, but it is available.
Is that an issue? I mean, I notice a lot is in terms of what we do in scheduling, we try and minimize data movement. Is that sort of part of Slurm? Is it like we're looking at like specifically like nodes co-located with a rack or racks like within the same SCIF in terms of moving data from one node to another, right? That's a big expense.
Right. Yeah. And in that case, you might very well want to have associated with nodes specific features like racks or file systems or whatever. And then when the request comes in, either have the user say, I want to run a rack 1, or somebody can say, I want this file system, and have like a job submit plugin and say, oh, well, he asked for this file system, that's in rack 1, let me explicitly give him one node on rack 1. Or one CPU, or whatever is appropriate. So here's a typical Linux cluster configuration where you've got a Slurm control daemon running with an optional backup. There's a database daemon available for the accounting records and configuration information. And again, that can have a backup. We recommend using MySQL, and your accounting records are here. This database daemon does two things for the accounting records. One is when we send information about jobs completing, we're not sending it one by one, so we'll package it up and send a message across with however many job records we can, or if a job starts and terminates in close succession, we can combine that information. And the Slurm database daemon has a password for, or can be configured with a password for MySQL, and you want to protect that, and this is one way to do that. The other thing is if somebody's updating resource limits, say I want to limit Ralph to no more than 10 jobs running at a time. When somebody updates this information in the database, this database daemon will push it out so that the entity, the Slurm control daemon that's making those scheduling decisions, know that some limits just changed. On each of the compute nodes, and we would have a Slurm, what we call a Slurm D daemon. It's very small, it's very lightweight. We have hierarchical communications for performance reasons, and the communications network is is fault tolerant, so if any of the nodes go down, it'll route messages around it.
Well,
Yeah.
on your daemons, do they sense and report back what the local topology is, or is that a configuration thing that you have to tell Slurm?
The topology with respect to within a node in terms of like the board, sockets, and cores, the slurmd recognizes that. It uses HWLoc, which you're probably familiar with, and it sends that information up to the Slurm control daemon. In terms of the network configuration, you need to, if it's a tree type communication mechanism, then you would be responsible for constructing a configuration file with that. If it's a 2D or 3D torus, you just need to define that and it'll figure it out. So if you're running multiple clusters, typically you would use a single database for all of that and a single database daemon. And your user tools would let you submit jobs to multiple clusters and status jobs across those different clusters. I've talked a little bit about the daemons. I'll get into them in a little bit more detail here. So Slurm CTLD or control daemon, typically one per cluster with a backup. It monitors the state of your resources, your queues, allocates resources, collects the accounting information and sends that off. The slurmd is what runs on the compute nodes, except on a Cray and a BlueJean it's a bit different. That they run on front end nodes. So this is actually what launches the tasks. Very small, very lightweight. After it launches tasks, depending on your configuration, it typically just, it's completely quiescent. It doesn't do anything. And it supports the hierarchical communications. Slurm database daemon, typically one for the entire enterprise, and that's what's handling all your communications with your database. And again, that'll have an optional backup. Your daemons all have a few options, and if you're starting this stuff up and you're doing debugging, this might be useful for you. There's a -C, which clears all your previous state. So say you're messing around, things got into some bad state, you want to just throw it away and start clean. -C. -D runs in the foreground and writes your logs to standard out. So for debugging purposes, that can be handy. And -V is to run the daemon in debug mode, and each D roughly doubles the number of messages. So if you're debugging, you want to see what's happening. Here are commands basically to run it in the foreground, clear all your state, and run it in a relatively verbose debug mode. For your compute node, if you want to see exactly what your configuration is, and I already mentioned to Ralph, this comes from HWLoc. If you start the slurmd with the -C option, it will show you what it sees in terms of disk space, cores, board. Actually, it isn't listed here, but the latest version has a board count too. One other thing that's not really a daemon is Slurm stepd, and this is what shepherds the user tasks when we launch them. There's one per job step. It's spawned by the slurmd, and this manages the tasks. It handles all of the I/O for the task. So the slurmd itself spawns it and then just leaves it. This typically runs in the same job container as what it spawns, so it's bound in the same memory footprint and to use the same CPUs as whatever it's launched. And it only persists while the job step is active.
So it's fair to say that slurmd runs at root level, right?
Yes, and the slurm stepd runs as user
level. Okay,
Exactly.
so all the I/O is going to a user level process to
Exactly.
fix security issues. Yeah.
I have a question here.
Sure.
This question may be both asked, right? Because OpenAPI has a daemon, has a own daemon, and this Slurm study maybe they have same functionality, yeah, of the OTD. So how can we process such things?
Why is there an Orte daemon as well as a Slurm step daemon? Because
I can stand you.
oh no, I can hear. You can hear
Okay.
on a good microphone there. It's a historical reason. First off, OpenMPI will run both ways. You can launch the processes directly using the Slurm step daemon, or you can have the Slurm step daemon launch an Orte daemon and let the Orte daemon handle the process, launch the processes themselves. The difference between them is that if you have the Slurm step daemon run the job, then you can't use MPI2 semantics for spawning additional processes. Your initial job is the only thing you can run. If you want to do a dynamic launching of processes, so you have a job that's going to launch additional processes itself, okay, then you need to have that Orte daemon in there so it can handle that additional spawn call. So
Actually, Slurm has mechanisms of doing that today. And the other thing is, you're talking about open MPI. Slurm supports many different flavors of MPI.
So there's it's there are lots of ways to do it. Is the best way to answer it. And so when we originally wrote it, there were things that Slurm didn't do that we wanted to do that we went ahead and did it one way. Slurm now has those things. We could go ahead and take that out if we wanted to, but we need them for other purposes anyhow.
And other resource managers.
Other resource managers, yeah. So it's kind of a...
It's this big matrix of resource managers, of MPIs, and everybody's got to work with all the different flavors.
When we first wrote OpenMPI and distributed it, we did not support launching directly with Slurm. And it wasn't because we didn't want to or anything else, because nobody had the time to worry about everything else, and so we had needed the other way of doing it for RSH launches and other resource managers. Okay. So it's kind of been an evolutionary thing, and over time I think we're taking more advantage of Slurm and decreasing the times when people run with the Orte daemon on a Slurm machine, but it's still there as an option.
Okay. So what you mean is, currently we are using Slurm launch the OTD first, then OTD will launch itself process, and in the future maybe we will not do like this. We will all use Slurm launch everything and manage it by ourselves.
Well, currently we support both for OpenMPI. Yeah. Okay, now talking about, because like Mo says, there are lots of MPIs out there. Okay, currently we support both methods of operation with OpenMPI. You can have Slurm launch the processes, or you can have OpenMPI launch the processes. There are some minor differences in features between the two methods, all right, but they both work.
So your logs, each of the daemons writes its own log file, and there are configuration parameters that say where the log file's written. One thing you should know is that the Slurmd log files that can include a %n, which is replaced by the actual node name. So this is a convenient way to keep track of where the log is from. There's a debug level configuration parameter that controls how verbose it is. It's like the -v's if you're starting up your daemon on a command line. Important messages are also written to syslog. And yeah, you probably want to configure log rotate too, so that if your logs get really big, something will compress them and move them out of the way. Otherwise, you could potentially fill up log files. Besides that -v for generic verbosity, there are also 17 debug flags available. So if you want to generate detailed debugging information about just a specific subsystem, that's the mechanism you would use. So if you want to get specific information about what the backfill scheduling algorithm is doing, you can turn that on, and you can you can change these on the fly on a live system. Say, I don't understand why this job's not running. Well, let me just change the debug flag, let the backfill scheduler run once or twice, turn it off, and then study the logs and hopefully figure out exactly what's happening.
Question, what type of admin tools do you have on top of this? Do you have stuff to extract, like look for nodes that might have failing disks, or that, like, say, the CPUs run slower for some reason? Any type of analysis like that?
There are fairly extensive logs available. In terms of tools, I'll be honest, it's not as extensive as it could be. Something that Slurm does have, which I know a lot of people have found useful, is we're keeping track of CPU use and memory size on a per task basis. So if you're running a parallel job, say it's 64-way parallel, and one of your tasks is using 10 times as much memory and 3 times as much CPU as the others, you can find that from the Slurm logs.
Okay. I mean, that's of interest to us, right, in terms of, you know, you're looking for hardware that's deficient for some reason, right, and wanting to be, you know, to find it in your cluster.
Yeah. A lot of, well, most sites run job prologue and epilogues also, which you can use to potentially find problems. There's also a health check script that you can run on a configure in Slurm to run periodically to look for anomalies. So now we'll get into the user commands. So general information about the commands. There are man pages for all the commands and daemons. If you type --help, it'll print a brief description of all the options of that command or daemon. So if you forget, it's an easy way to get it. --usage just prints the options. It doesn't explain what they do at all. The commands can be run on any node in the cluster. If any failure happens, when you submit a job, if something fails, or you want to status a job and it isn't found or whatever, any sort of failure results in a non-zero exit code. And there are APIs available for all the functions that Slurm does. So if you want to develop your own version of a tool to look at accounting records and fish out whatever type of information you want, or submit a job. Actually, somebody in China just recently submitted a problem where there was a bug in one of the Slurm APIs related to job submission with certain options. And there are man pages available for all of the APIs too. So most options have 2 formats. There's a brief single letter format. So -p debug is for when you submit a job, say run it in partition debug, or you can spell it out --partition equals debug. Your time formats are well, day -hours, minutes, seconds. I won't get into the details in terms of, well, I mean, if you just use a number, it would be minutes. Number : number is minutes, seconds, but that's all spelled out in the man page. The commands support -v as well for more verbosity. And there are environment variables available for site-specific or user-specific defaults. So for example, SQ is the command that's used for printing information about the jobs in your system. If you want to automatically see information about jobs in any state, even completed ones, you could define an environment variable, SQ states equals all. And you would just automatically see the state of all the jobs in the system. So for job and job step allocation, the commands you would use are sbatch, which takes a script and use it to submit a job for later execution. salloc is an interactive mode. You specify the resource requirements, and typically the command you would run would be a shell. So salloc -n16, give me 16 CPU's bash. So what'll happen is as soon as it gets those resources allocated, then you get the bash shell prompt, and it has various environment variables set up. So at that point, you can launch your MPI job within that allocation. srun, if it's running within an existing job allocation, in other words, it's run from within sbatch or salloc, then it just launches the job step. If otherwise, it creates the allocation before launching the job step. sattach will connect to an existing job or job step. So say you've got an MPI job running and you started up at work and you're at home and you want to see what's happening. So you can log in, you can attach to that running job, you can get recent standard out and error and say, I don't like what it's doing, I'm going to, enter some input so you can steer it. Some examples here, how many tasks you want, runtime, and the script to run. This lists dependencies, so here's a sequence of 3 jobs with different time limits and to run your pre-processing, your main work, and your post-processing. Just a real simple example of what a batch job submission would look like. For a job allocation and job step allocation, the -- label prints a task ID : before the output. So this just launches 2 tasks to run hostname. You don't necessarily need to run an MPI job. You can run a shared shmem or whatever. Here's another option where you specify a number of nodes with exclusive, so there's nobody else that runs on them, and you see your output from 2 different nodes. Very simple examples.
So in the first one, you told it to run 2, but because you didn't say exclusive, it chose one node to do it.
It will try to put the tasks close together. So, it will, ideally put the, if you've got it configured so that each task can run on a separate thread on the same core, it'll try to put these on the same core for you. All right, if you can't do that, I'll try to put them on the same socket, board, etc. And like I said, there are options to control that. This gives you an idea of what some of the environment variables are. I already talked about salloc, so I want to run 4 tasks, 10-minute time limit, spawn a shell, and then after the resource allocation takes place, it says granted the allocation, your job ID, and this just shows you some of the Slurm environment variables that are set up. So when srun runs or some various flavors of MPI or whatever, they can look at these and figure out what resources are allocated to it. And then when you exit the shell, the resource allocation is returned. Slurm has the ability to run different executables by task ID. So if you want to run in a master-slave type operation, you might have a script that looks like this, where task ID 0 runs this master, and task ID 1 through 4 run a slave, and the argument to the command is this would be a task ID. Just a simple example as to what that would look like. MPI. I already said we support many different flavors of MPI, and some of these have Slurm plugins for them. Others just work without any plugin. Some rely upon MPI run or MPI exec or run job or something else to launch the tasks. In other cases, you would use srun, the Slurm tool, to directly launch the task. And the web page spells out exactly how to run jobs with different flavors of MPI on Slurm. Now to go through a job launch sequence, So we're doing an S-run, say we don't have a resource allocation, sends a request to the Slurm control daemon. When the request can be satisfied, a response is sent back to the S-run. Then the next step is, that's for the job allocation. For the step, the S-run sends a request to launch the step, and the Slurm control daemon would basically instantly respond with the job step credential, which is used by the S-run process to launch the test. So the S-run is going to open up sockets for I/O and forward the credential to the Slurmd on the first compute node that it works with. That in turn is going to forward that credential to the other nodes. Slurm stepds are started, so the Slurmd is running as root, the Slurm stepd is running as the user. The stepd is going to spawn the user tasks and connect back to the S-run for the I/O. And that's also used for signal handling, that socket. When the task completes, the stepd notifies the S-run, and the S-run notifies the Slurm control daemon. Only at this point does the Slurm control daemon actually talk with any of the compute nodes and say, this job is done, run the epilogue, make sure all the processes are gone, and when they're gone, I'll reallocate the resources.
Well, is there a wire-up step in there in the Slurm stepds to wire them up so they can collectively communicate, like through PM, or I'm not sure. I mean, PMI doesn't go through the Slurm stepds, correct?
Right. Basically, it's handled by the Slurm library. So yeah, what happens is the Slurm stepd, the Slurmds, these are not persistent connections. All right. For the I/O, the Slurm stepds are connecting directly back up to the S-runs. The other Slurm commands of interest, sinfo reports the system status, so what your queues are, the node state. SQ gives you information about the jobs and steps. SMAP reports it reports job and step and system information, but it uses a curses-based GUI, and I'll show you an example of that. So this includes topology information. SView is a more current topology-based tool, and it has mechanisms of submitting jobs and changing state. And scontrol is a system administrator tool. I'm going to go through all of these and give you examples of them all. So sinfo, like I said, reports node and partition state information. So just a simple example here. I already mentioned how Slurm uses a regular expression to condense node information. Here's an example of that. You can also get information on particular partitions. -I says iterate, redo this every 60 seconds. There are options available which you can either set on a command line or by setting environment variables that control exactly what information you get, the format you get it in, how it's sorted. So you can make these tools look like pretty much anything you want for the system or job information. SQ, quite a few different filtering options too. So for example here, giving information about jobs belonging to user alloc in any state. So this is a default output. If the job is pending, rather than having information about which nodes it's been allocated, it gives you a reason why it's waiting, whether it's waiting for resources, waiting for a dependency to be satisfied, waiting for because they're higher priority jobs waiting or whatever. SQ also reports information about your job steps with the -S option, and I already mentioned how a job step format would be a job ID period and then a step ID value. This is the sview command on a Cray. Cray typically has a 3-dimensional torus or some with 2-dimensional torus. And each of these dots represents a Cray node. So what you're seeing here is a representation of how well packed the resources are for jobs on this Cray system. So each of these represents a node. This is the X dimension, the Y dimension is that way, and the Z dimension. You can picture each of these as basically cards that you can flip up and stack up like a really big Rubik's Cube. And so the red job here, you can see that it's all of its resource allocations are relatively close together. I mean, it's 4 in this dimension, 4 in that dimension, and it looks like, I don't know, maybe 16 in that direction. This is the S-map, which is a curses-based option, which you can't quite make out as well, but again, this is a Cray system, and each one of these planes represents the nodes and which jobs are running on them. Afraid it doesn't show up so well on this screen. S-Control is a tool designed for system administrators. It shows all the available fields, but there's no filtering or sorting or formatting options, so it's kind of a bare bones type of tool. But it's also good to work with, you know, other programs that you want. If you want to use output for a scripting language to do sorting or whatever. Actually, one other thing I'll mention, I'll go back here to sview. There are many other fields here. You can control which fields you get, how they're sorted, their position here too. So there are a lot of options here to control what you see with sview. For accounting, the tools available are S-Account, which reports information about individual jobs and job steps. SStat reports information about currently running jobs and job steps and gives you more information than we archive. And S-report gives you aggregated information, so information about all users at in certain groups, how much time were used, or how much time was used by this particular user without getting information about each of the individual jobs that was run. So here are some information. This doesn't show you the output, but you know, give me information about all jobs run by user Joseph, or all jobs run in partition debug, and it will list, you know, Lord knows how many jobs at that point. There are obviously time options for this too, so you can say just jobs that ran yesterday or ran the last 5 minutes or whatever.
I have a question here.
Sure.
Did the Slurm have a machine that can support user provided accounting
Information.
informations?
Well, in terms of the information which users can supply for this, there's something that we called a WC key, or workload characterization key, which is an arbitrary string, and that a system administrator can require that users submit jobs with a valid one if you want, and that's another way of characterizing the work besides the partition or QoS or username. So if you're doing work on, pick a project, say you work for Ford and you're working on a new, you know, car, well, I don't know, their new Taurus or whatever, you might have a WC key of Taurus, and everything that's done related to that would all have that workload characterization key, or WC key.
You mean users can using an API to load something to this accounting system, and this account can.
Well, this would be information that users provide when they submit their job. In terms of information that users can submit afterwards, there are also tools to keep track of if jobs fail and if they don't. So, for example, I talked about job steps, all S runs. I mean, Slurm uses that information and it captures the exit state of each one of those, and whichever one is highest, it uses that as an exit code for what we call a derived exit code for the job as a whole. And users can go back and change that. They can also put arbitrary descriptions in. So a user might, for example, say, this failed. I think there's something bad with node, tux 1, 2, 3.
But generally, when the user submits a job, it's not like the job uses a Slurm API to write stuff to the Slurm logging mechanism.
No, I mean, users can submit, there's also a comment field that users can submit with their job, which they can put arbitrary stuff in. So there are a number of places where users can attach things to their job, which could be used for accounting purposes later.
But like if the user job runs and the user wants to log, I mean, you're saying that's generally a separate mechanism.
Well, the only mechanism we have available to the user after the fact is a mechanism which is oriented towards failure characterization. And on exascale machines, that type of information can be really valuable. Some of the tools that are available for scheduling purposes, there's S Account Manager. This is your tool available to manage the database, add, delete clusters, accounts, users. I'll get into more description of that, I think. S-Prio. So when jobs are in the queue, there are various factors that contribute to how the priority is set. And this breaks it out in terms of how your priority is calculated. S-Share is a mechanism of viewing your current hierarchical fair share information. And SDiag is a tool for viewing statistics about job scheduling. Your average queue size, your average execution time of the scheduling loop, number of jobs, percentage of your jobs that are started through backfill and so forth. In terms of your database use, this shouldn't have been split here, but besides the accounting information, there's information about quality of service, sorry for the split here, fair share resource allocation, I'm pretty sure I got a picture of that afterwards. There are a multitude of limits which can be set on a user, a group, and also aggregate limits. So you can say, I want to limit this group to no more than 10 running jobs, and I want by default to have every user in there have no more than 2 running jobs at a time, but Ralph's special, so I'm going to let him run 4 jobs at a time, things like that. And also we've got a concept of bank coordinators. And what a bank coordinator is, it's a person who's in control over the database information, the limits and users for a bank and everything under that. So he has the ability to change these limits and shares for people in his domain. Here's a simple example of a hierarchical bank where your root has 100% of the resources, and we have, say, 3 divisions. This can be arbitrary depth, incidentally, and Division B has 3 groups, and various users are allocated a share of the resources there. And like I said, users can be in multiple places. So if Pam is doing work for group beta, she'll have 20% of that, but if she's doing work for group alpha, maybe she's got 10% of that or whatever. And you can have one bank coordinator for division B and a different coordinator for group beta that's able to control different sets of people in terms of limits and the shares. A few of the other commands, scancel, which you can use to signal or cancel job steps. sbcast is a tool used to transfer files to the compute nodes, and that uses the hierarchical communications I already talked about. There's srun-cr, which is a wrapper for the srun command for support of the Berkeley checkpoint restart. And strigger, I didn't really talk about triggers, but Slurm supports maybe 30 different triggers. So system admin can set up a trigger, so if a node goes down, it runs a script that sends an email, for example. Or a user can set up a trigger so that when his job is within 30 minutes of reaching its time limit, runs a script that sends him email so he can go check on it. scancel, pretty simple. I mean, by default, it terminates the job. It sends a scontinue, a sigcont for continue, sigterm, and then after a configurable period of time, it sends a sigkill. You can also specify other signals to send. There are a multitude of filtering options, so you can say cancel all the jobs belonging to user alloc that are in a pending state. sbcast, this may very well not be applicable for you here, but if you've got diskless system nodes and you don't have a Lustre file system, or maybe if you do, you can use this to transfer files to your compute nodes. Trigger, you can use this to create triggers, view them, cancel them. Useful for mostly sysadmins, I think. So he can be notified if bad things happen. So now I'll get into the build and configuration. So we have the Slurm tarballs available at SCEDMD at this location. We release a new minor release about every 9 months. And in between that, we release micro releases with bug fixes. So your APIs, your commands, basically, they only change at most every 9 months when you come out with a new release. Between that, whenever we feel there's enough changes, and we feel things are in a good stable state, we'll tag a micro release. All of our work is in GitHub, so if somebody wants to see what we're doing day by day, minute by minute, they want to get the very, very latest code and they want to live dangerously, it's all in GitHub too. I would recommend using the tarballs unless you're doing very active development. Some of the tools you typically need are Munge, that's the default authentication mechanism. And if you're running with Java counting or limits, we recommend MySQL. So your build procedure is pretty simple, just RPM build and then the tarball, and then you install the RPMs. There are a total of, maybe 20 RPMs. I mean, some of these are system dependent. So for example, if you don't have a BlueJeans system, you don't install the BlueJeans plugin. You have a Cray system, you don't install a Cray plugin. So this just goes through the various plugins. The ones I have in red here are ones you probably don't want to use. We have Perl APIs available. Again, if you're not using the database, you wouldn't use these. We have command wrappers for torque PBS, so if you want to use use psub and commands and such, you can do that.
Yeah, I recommend avoiding AI systems.
We haven't built on an AIX system for a while, but we have worked on the IBM PERC systems, and that was getting back to IBM systems quite a bit. So on a typical system, you might install, looks like 3, 4, 5, 6, 7, 8, 9 plugins, and that would be a pretty full configuration with all the accounting and database stuff. Whoops, dice. Oh, so if you don't want to build the RPMs, if you're actually doing development work, uncompress and unpack the tarball, you can execute build, configure, and this lists some of your typical options, and then make install. So if you're doing development work, the advantage of doing this rather than RPMs is typically you would be modifying, say, one daemon or one plugin, and you wouldn't need to rebuild it. You would just make and make install on a particular subdirectory, say that particular plugin, as you're doing development work on it. And here's an example. When you run make, don't forget the J, so it builds it in parallel. Otherwise, it'll take quite a bit longer. Actually, worst case, I can build everything on my netbook with a single core Atom processor in 13 minutes. So
that's worst case?
That's worst case.
You're doing make minus J, what is that?
Yeah. So, I mean, if you get a sizable machine, an i7 or something like that, and it'll build in something more like a minute and a half. Your Slurm configuration file is called slurm.conf, and it's required on all the compute nodes and service nodes, basically anywhere a daemon's running or a command's running. Most of your parameters have usable defaults, but at least the nodes in the cluster and their grouping in the partitions or cubes or queues need to be defined. There's a web-based tool available for you to build this configuration file. There's one called, this comes with the Slurm distribution. One's called Configurator. And if you want the bare bones one, there's a Configurator Easy where you basically need to make half a dozen choices and click generate, and it'll make the configuration file with it for you. And just save it. There's a man page for the configuration file with slurm.conf to give you more help. So here's an example of what the tool looks like, basically spelling out what it does and what your head node name is, and it defines exactly what's optional and what's required. Just an example. It's pretty straightforward to use. Your configuration file, when it's done, is going to look something like this. It'll say how it was generated. You want to put it on all your nodes. Your head node. Anything that starts with a pound is just a comment. Something else I'll mention is your configuration file can include other files. So if you want to have a common configuration across your enterprise, but just want to have differences with compute node and head node names, your configuration file might just have include your common portion, and then whatever your differences are in each of the nodes. It's defining, for example, here your authentication plugin. What you use for digitally signing your crypto plugin, and several of the plugins can be stacked, so you can list multiple plugins that get called in a specific sequence. Yeah.
On that, if I have an include of something, say in
Yeah.
a high-level system, and then can I override a value, or do the values have to be unique?
I am not certain if they need to be unique. It either will complain and say you got a duplicate, or say, oh, you've got a duplicate, I'm going to use your latest one, or maybe it doesn't complain. I suspect it at least tells you that you've got a duplicate, but I'm not certain. Your authentication mechanism we recommend is Munge. That's open source GPL2. Each cluster needs to have a Munge key and the daemons running. And this is highly scalable. Basically, the way it works is Slurm gives it a payload, and that includes things like the nodes, and it digitally signs it saying, the user number came from the group ID, a timestamp. I'll mention that the timestamp component necessitates that all your nodes be running with a similar time. I won't say exactly the same time, but if they differ by multiple minutes, Munge is going to erp. Slurm will run, but Munge will complain. And you can also configure Munge with multiple keys, so you might have one key for use within a particular cluster, and if you're going to be if there are going to be messages going between clusters, you might use a different key for that. So for users submitting jobs between clusters or statusing between clusters or whatever, that just provides you a little bit better security. Slurm includes a test suite. It includes over 300 test programs that executes thousands of jobs and tens of thousands of job steps. So if you're changing the code, you want to validate nothing broke, this is a good thing to do, and we run it regularly with different configurations on different system types. So usually we find out pretty quickly if something breaks. Before you run it, you have to set up a configuration file saying where Slurm's installed, where it's built from, and where your source code is. And typically what I do is there's a script called regression, which basically drives the whole thing, and I will typically send a standard out to some other file, and then the standard error will come here, and it will print details about which specific tests failed, as well as how long it ran for and so forth. And if failures happen, if you look in your log file, if you look for the uppercase word failure, it will take you exactly where the failure occurred, so you can find it. Slurm can also be configured to emulate different system architectures and different system sizes. We actually did a lot of the Blue Gene system development on laptops because we didn't have access to a machine for quite a while. We did a lot of work on a port to Craze, just using laptops and desktop systems too. And before we even had access to a machine, we had the plugins written. We were selecting nodes. We just didn't have the hooks fleshed out to talk with Alps underneath. So, there are limits in terms of scalability, but if you want to emulate a large cluster, thousands of nodes, different scheduling algorithms, features and whatnot, just do sleeps with your jobs. Don't run real MPI jobs, but you can certainly test your configurations and resource allocation logic. The last thing I'm going to go through is some more details about the scheduling plugins in Slurm and some information about Slurm development work. So one of the plugins we've got is called Priority. It basically decides the scheduling priority of pending jobs. And there are 3 available right now. There's a simple first in, first out scheduler, which basically just counts down, has a counter, and as jobs come in, it just gives it a lower value for each job. There's a multi-factor one. So this sets the job priority based upon its age, which queue it's in, the size, so you can favor larger or smaller jobs, the quality of service, and also fair share, so how overserved or underserved a user is. There are a lot of parameters for these various things too, so not only can you control how important is a job size compared with its age, but when you're considering the age, what the maximum age is at which you want to give a job whatever the maximum is. Or for size, if you want to favor small or large jobs, what exactly constitutes a small or large job? There's also, this was recently added, a multi-factor 2 plugin, which is similar to the multi-factor, but it's a ticket-based variant of the code, which I won't get into the technical details. So if you wanted to define your own scheduling plugin to prioritize jobs differently, probably you'd want to grab one of these and use it as a model. You wouldn't have to build your own, but I mean, you would have to define all the functions. I don't know how what your concerns are for prioritizing work, but this is where the prioritization happens. Scheduling, I already talked about this a little bit. To select linear is to allocate whole nodes. The next one, which was developed by HP, is select consres for consumable resources. And again, this added the ability to allocate resources on a much more fine-grained basis, almost all within a Slurm plugin. It also takes into consideration your network topology. I already discussed the Blue Gene and Cray. We've recently developed something called Select Serial that is highly optimized for serial jobs, by which I mean single CPU jobs. And this actually, if you're only running single CPU jobs, you don't have to worry about placement of tasks within cores and sockets and so forth. So, one of our customers was trying to get as much performance as possible out of it. There's a plugin which controls preemption, and by that, this defines which jobs can preempt which other jobs and what the preemption rules are. So you can completely disable preemption, you can preempt based upon quality of service or the partition, and you can also define what the preemption rules are. So you might have, for example, a quality of service defined as standby, really low priority stuff. When you preempt those jobs, maybe you want to requeue them or cancel them. For a higher priority job, maybe you want to only suspend it and then resume it when whatever the preempting job is, whenever that terminates. And Slurm will take into consideration if you're suspending it, you're not releasing the memory, so you need to still have enough memory to fit both jobs on the node at the same time. Sched controls the scheduling order. I mean, the priority sets the priority of the jobs, but after the jobs are prioritized, there's a built-in which basically just takes the jobs in order. There's a backfill plugin. When this is started up, it starts up a separate thread that, depending on what your configuration parameters are, it will go through the queue periodically and determine exactly where and when the pending jobs can start. And Slurm uses a conservative backfill, and by that I mean no job will be started out of order if doing so will delay the expected initiation time of any high priority job. not just the highest priority job. And there are a variety of options available, how far down the queue you want to look, how frequently you want to do backfill scheduling, and so forth. For development, most new development happens in the plugins rather than in the kernel of the code, just because it's a whole lot easier. We encourage you to coordinate any development work with us. There have been a number of instances where people say, "Oh, I want to work on whatever." We say, "Well, this other company, university, is already working on it. Let's get everybody together and collaborate." We follow the Linux coding style, and what I've seen so far coming from Greenplum is more or less following that. Also, when there are code changes, try to keep the documentation current. So if there are new functions added to a plugin or new configuration parameters or whatever, try to keep the documentation current. We release Slurm under the GPL version 2 GNU public license. So your work has to conform with that. So I think that is actually, all right, one more. This is just the basics, so there's lots more documentation online. If you got questions, in your case, you can send mail directly to us, but there's a developer mailing list which has about 350 people on it. We've got a Bugzilla system, so if you encounter a bug, you want to report it, this is a good way to do it and for everybody to track it. And if you report a problem, please indicate the Slurm version number, because sometimes people are reporting bugs that have been fixed a year ago, configuration details, because like I said, a third of the code is in Slurm plugins, and if we don't know what plugins that you're using, we might very well not be able to reproduce the problem because we're not using the same code, log scripts, and so forth. So, I think I just about nailed the time, didn't I?
Thanks.